right, let's just do this. It'll be fun. Hi, fellow geochemists and geochemistry enthusiasts. Welcome to Geochemistry, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire and to shed light on the topics not fancy enough to talk about at a conference, but important to delve into. I'm your host, Sam Scher, and this week we're expanding on our original talk with Simon Griffiths on the geochemistry of Carlin systems, and now we're going to be talking about high sulfidation epithermal systems. Simon Griffiths is the principal consultant at Third Planet Exploration Services. Simon, welcome back to Geochemistry.
Thanks, Sam. Great to be back.
Simon was on our show as our first guest. So we went through your journey into geochemistry there at length. If anybody's interested, please see the Carlin podcast that we did. And really, more or less, what we got out of that was that you're the only person who knew how to use a computer at Kennecott. At least that's how I remember it. So a year and a bit later, I was wondering if you could share with our audience any insights you have for those who want to pursue geochemistry in the exploration or mining industries. And where do you think today's geochemist starts?
Great question. Look, if someone is really interested in getting into exploration geochemistry, working in the mining industry, I'd really encourage them to get online and look at some of the podcasts and some of the webinars that have been put out in recent years. I think there was a bit of an explosion with webinars a couple of years ago with everybody being locked down. And so there's quite a lot of information out there now. Some of the recent conferences that are not virtual anymore have also published the speeches or the talks that people have done. So there's quite a few ways to get started on it. And then they could probably reach out to companies or people who are doing geochem interpretations around the globe and try and get some mentoring. If people are still in university, then I think they should look for either an industry mentor or try and identify somebody in their geology department that can steer them maybe towards some of the more pragmatic sides of exploration geochemistry.
You're not wrong there. I know that when I first started out, what I had wasn't necessarily a degree in geochemistry, but my master's involved geochemistry. But when I first started out, I had two mentors, one of which the company I was working for paid for, actually. And after that, I just continued to collect them. And I think that to understand how exactly we're applying geochemical and even statistical principles in industry, it's so important that you cut the line and don't have to reinvent the wheel. And honestly, this is what this podcast is all about. So anybody that's been on the show, a lot of them are super open to people that have questions reaching out. And then maybe from there, one thing leads to another, and you get your own Simon Griffiths as a mentor. You'll have 50 students.
Look, I'm right into that, Sam.
Awesome.
I mean, look, over the years, I'm definitely open to that. Over the last few years that I've been consulting, I've probably worked with about half a dozen students from different universities, mostly in the UK, but also around the world. I've helped them out. Some of them have done some summer work for me. I've shown them a few tips and tricks in iogas, a few tips and tricks about exploration geochemistry. And then others have stuck around a bit longer and worked with me for over the course of a year or so. The other thing that actually happens sometimes with me is that as I go around to site on part of my consulting job, I'll often come across some younger geoscientists, early career geoscientists at the sites, and sometimes one of them or a few of them will reach out and ask me for some advice. I'm mentoring a few young geologists or geochemists around the various sites I've been working at, and like I said, I'm always open to helping somebody out. I think we all need a break. It's tough to get into the industry, and as long as there's a bit of mutual sort of support where they can help me out and I will help them out, that's just great.
And there you have it, guys. Very cool. So moving on then, I think it's that time of day where we have the kettle hot on the stove and it's ready to spill some tea. I know that you've already spilled some before, but let me tell you, nobody here at Geochemistry is immune from sharing a good cup of tea. And I was thinking that instead of leaving this completely up to you this time, because we're talking about high sulfidation systems today, is there any kind of tea that you can bring us that involves maybe one of the sites that you visited, one of the sites you worked on? You don't have to name names, but maybe that might be a little bit fun.
Yeah, okay, Sam. Well, I'm not sure if it's too shocking, but the deposits in South America, the ones in Chile and Argentina, kind of line up right along the border between those two countries. And the border between those two countries is essentially defined as the highest point between them, or the watershed. There's a lot of other mountains around there that are pretty high, well over 6,000 meters, and the mountain passes are pretty high too. So I always remember traveling up by car to Veladero, which is in Argentina. Basically, you fly into a place called San Juan, and then it's about a 7 hour drive or something. Anyway, part of the drive, you go over one of these mountain passes. The company I was working for at the time, we had a rule where nobody was allowed to go to sleep in the truck for safety reasons. You know, the driver then might feel a bit drowsy because everybody else is asleep. So we were supposed to be chatting with the driver all the time.
I am dying listening to this.
Right.
Continue.
All right. So on the way to Veladero, there's this really high pass, and there's a big sign on the road that says the driver must wear an oxygen mask or have oxygen up their nose as they're driving. So, of course, they stop, they've got a canister of oxygen in the truck, they put the mask on or put the little tubes up their nose, and they continue driving. So they're on oxygen. So what do you think happens to everyone who's not on oxygen? Like, so the rest of the crew in the truck all just pass out basically. And just leave the driver by themselves driving up this mountain pass and down the other side.
So was this in any kind of safety share that we did at any
Well,
point?
yeah. So, but these are two safety rules that basically
Oh my
conflict
God.
with each other. Why don't we all have oxygen masks?
Indeed.
But then you can't talk to the driver anyway because you got a bloody mask on.
I mean, at least maybe you could poke them, sign language, something. Oh
Yeah.
my God.
So that was always a bit of fun.
That's unreal.
So the last
I
thing you
remember,
see is,
yeah.
please wear an oxygen mask, and then you wake up at the mine.
Wow. My recollections of being on oxygen as well is it makes you a little loopy as well. I definitely commented to the doctor at El Indio about how attractive he was, and that was completely unprofessional. But in my mind, I thought it was a really good idea at the time. So, oxygen.
Okay.
Okay. Anyway,
Cut
there you
that.
have it.
Cut.
Okay. So, high sulfidation deposits in the high Andes. We love it. Love it.
Yep.
Two great topical stories. After the resounding success of our Carlin episode, I asked Simon back on the show because geoscientists everywhere have been asking for more on the geochemistry of ore deposits, and his episode is still our most listened to with almost 500 listens at this point. Congratulations. No big deal. Yeah, exactly.
It's just what I do.
Woo! Simon has worked in a variety of deposit styles, but as high sulfidation epithermals were my first love, and he's had extensive experience in them, we thought, why not dive into them? After creating the initial episode outline, Simon and I chatted and we meandered towards two papers written for Exploration 17 about the Altura's high sulfidation epithermal discovery. If you've not read them yet, start with the Astorga paper for the overview and then follow up with the Zhao paper. Simon, I've given now my intro to high sulfidation epithermal, but let's get into why you wanted to base our discussion around the integration of geochemistry and spectral data into a robust high sulfidation epithermal exploration today. Hype us up.
Yeah, that paper, I was involved with writing it as well, but I think that paper really is a nice summary of integrated exploration resulting in quite a big success. That deposit, I think the paper mentions it's just under 7 million ounce deposit at a gram per ton. And the mine I was just talking about, the operating mine at Veladero, at that time was running an average grade of 0.7, I think it was, grams per ton. So you just got to move an awful lot of tons. But anyway, it was at the stage of exploration, it clearly had a big potential to be an economic mineral deposit. So those are a big success for the team. I was involved for a few years from the early days at Alturas, because as the geochemist for Barrick, I was part of the technical support team. But later on, when we actually wrote the paper, I was based in Chile, and as the chief geologist, I had the technical team reporting to me. This paper is a culmination of all of the work from the entire technical team. So we had a spectral geologist, we had a geophysicist, we had a sort of expert geologist, and a geochemist, of course, as well. So Danielle Astorga was the project geologist on Alturas, and then the rest of us were the technical team. In fact, I send this paper to some people who were looking for other types of deposits, and I say, look, I know it's a different deposit style, and the actual geology side of it is a little bit irrelevant to what you're looking for, but just if you look through the paper, it describes how to organize a successful exploration project. It talks a lot about scale. It talks about the different exploration stages, and I'm all about the exploration stages and the different phases that projects need to go through, and the different scales and different type of sampling, for example, that we need to do, or that we tend to do at different scales, and there's different types of QA/QC that are necessary or more relevant at some scales than others. I think the paper really walks you through, and if you have more of an interest in the spectral side of things or the geochem side of things or the geophysics, then this paper has a little bit that everyone can enjoy. I think it's a pretty good paper. Yeah, I would say that.
Yeah, I would say so. I remember I first came
Mm.
across this paper when I worked for CoreScan because it
Mm.
was a great way for us to build up some of the business cases as well. So when you turned me around to put me back to these papers, I remember having enjoyed them the first time, but I think having read them now the second time and appreciating different parts of them that I wasn't looking for at first because I was honed in on the spectral piece of it. It's
Mm.
actually a really cool story. And I would recommend to everybody listening that you definitely have a look at these two papers. And even though the the Zhao et al. Paper gets really into the weeds here on the spectral component of it. I think that it's such an interesting story. And it's like you said, how the Astorga paper is how you do exploration at different scales. Spectral geology is really complicated as well. And this is also a guide towards how you both go through the different scales, even when you're within one scale, how you would look at different technologies that are out there, and then how you really would leverage having expert spectral geologists towards bolstering really interesting geological discoveries and geochemical discoveries. These two papers are really great, and I recommend them to everybody out there to have a look. And they're really not too heavy either, I have to say. Each one is what? No more than 7 to 10 pages, lots of pictures. You
Mm.
guys can do it.
Yeah, well, don't forget these papers were for Exploration 2017, and
Mm,
they were also presented orally. So the Astorga paper, I presented a 20-minute slot or whatever it was, PowerPoint presentation, and Xiaodong also presented her paper at the same conference. So they're designed as shorter papers
yes.
and that have accompanying presentations with them as well. So
Awesome. I really appreciate that introduction. And I'm going to start next with a bit of a softball question for everybody listening, because you never know when you get a geophysicist that wants to listen in. I've had some that have messaged me, so we got to start a little bit soft here. That said, so what's the general environment that we can find high sulfidation epithermal systems? What are they formed in? And to that point, could you also comment on any specific physicochemical conditions required for the alteration and mineralization?
yeah, okay, Sam. So high sulfidation deposits. First of all, we sort of envisage how they're formed. So if you envisage a volcanic, sort of hot spring volcanic geyser field, something like that, like Yellowstone or somewhere like New Zealand, you think of how everything's coming to surface and all this steam is being blown off and everything in these geysers. Now, low sulfidation deposits are what form very close to the surface, but a few hundred meters down, like 150 to 200 meters below the surface, or maybe a little bit more, where you get the groundwater interacting with the magmatic waters, that's where these high sulfidation deposits are formed. Okay, so from a geological point of view, when you're mapping in these volcanic fields, you want to, when in fact for high sulfidation and low sulfidation deposits, it's the same. You need to try and recognize, well, and VMS deposits, but anyway, you need to try and recognize the paleo surface. Okay, so you've got these basically syngenetic mineral deposits that are formed at a certain distance from the surface. So, for example, in the high sulfidation deposits, you want to try and recognize the alteration that you see at the surface of a volcanic field or of a geyser field and a hot spring field, and then essentially try and navigate down to a few hundred meters below, near where the water table, the surface water table or the meteoric water table was in contact or was mixing with magmatic waters. Okay. Now, from a lithological point of view, if the volcanics are too acid, so if the volcanics are too felsic, then they're not as reactive. So you've got a lot of silica already. Yes, you've got some feldspar, but when the alteration system comes in, if you've got very felsic volcanics, the low pH fluids are going to create some porosity, but not a whole lot of porosity in the felsic rocks. And if you have too mafic rocks or intermediate to mafic rocks, they're too reactive. So they'll be completely blasted through and there'll be nothing left of them if you have these hot acidic fluids come through doing the ground prep. So it's this sort of sweet spot in between. If you look at dacitic rocks, for example, they've got enough feldspar and amphiboles in them so they're reactive enough, and those minerals get basically dissolved away and space is created, but they've also got enough silica to maintain some kind of structure. So the early phase of alteration in these systems is normally extremely low pH. So there's a PhD on Pascual from about 20 years ago by Annick Coutard, and she's modeled where she's found that zirconium was actually mobilized in the system. And the pH, her calculations, they're less than 1 in some of these fluids. They're absolutely incredibly low pH. So you think about the water temperature is going to be 300 degrees because it's meteoric water, but it's mixing with magmatic waters. So they're hot and they're extremely low pH, so very, very acidic. So the ground prep there is these fluids coming through, essentially dissolving away everything except for the quartz in the rock, even having a bit of a go at the quartz as well sometimes. And then subsequent fluids that come through are pH is a little bit higher, so they're not as acidic. And now they'd be carrying silica, they'd be carrying gold, hopefully, and other transition metals and sulfur. And then those fluids are the ones that basically deposit the mineralization. So what you get in these cavities that are formed, the geologists call it vuggy silica. It's not vuggy in the sense that crystals are growing necessarily at the beginning, that crystals are growing into these vugs, into these voids. It's that the voids are created by initial ground prep. And then the silica that's in the subsequent fluids coats the edges of these vugs or these porous sort of holes in the rock and start to fill them in a little bit. So you can see some silicification in some of these voids, but you can then also see sulfides and other minerals getting deposited as well. So you need that sort of sweet spot of volcanic rocks that not too felsic and not too basic or not too mafic. And then, of course, the right level of interaction between the groundwater and magmatic waters. Now, the alteration footprints or products of these sequentially low and slightly increasing pH fluids are, but there's a lot of sulfur in the system. So high sulfidation, there's a lot of sulfur in the system. They generate a lot of alunite, which is a sulfate. They generate a lot of pyrite and other sulfides, because there's again the sulfide. And even if there's some sulfur left over and still a bit of iron kicking around, you might get jarosite as well. So in some of these deposits, there's been some debate about whether the jarosite is part of the epigenetic process or if it's some subsequent supergene type enrichment phase. But I think certainly you can definitely, there are some of the deposits that I worked on, there's a lot of evidence for the jarosite being part of a waning or a late stage of the actual mineral system itself.
Yeah, and maybe to plug myself, but also just because I loved it so much. So I said earlier how I love these deposit styles. For my graduate studies, I worked on an active volcano in Indonesia, and Kawiijan volcano actually has an actively forming not just high sulfidation alteration, which can be seen in other volcanoes around the world, but we also found that the pyrite there was mineralized. The pH of the fluids there were plus or minus 0.5 from 0, so negative 0.5 to positive 0.5. So yeah, these things are real acid in both the crater and then along the edifice that you could see this alteration. It was pretty cool to see something that was actively forming.
You mentioned geophysicists. Well, the geophysical expression of this alteration system, because there's so much quartz comes in and there's a lot of silicification, essentially they are large resistivity anomalies. So we used to do electrical geophysics, electromagnetics, and look for essentially sort of tabular looking resistive bodies. And whether they are subhorizontal or subvertical, depending on what's going on down there in terms of the plumbing, that's the sort of thing you're looking for.
We've touched on a lot of this stuff, but as a geologist, we're walking across the ground in one of these styles of environments. We've talked about a number of these minerals, but just to sum up everything, what indicators are we looking for in terms of these alteration, this gangue mineralogy, any kind of mineralization? We've talked about alunites, we've talked about some vuggy silica, some perhaps native sulfur. What are the other ones that we should be aware of?
On a mineral by mineral basis, the alunite is very interesting because the chemistry of the alunite seems to change. And of course, that's something that we can detect or measure with various of these spectral instruments. So again, we used to, all of our surface samples, and actually all of our drill samples, as a matter of course, we would collect 4-acid multi-element analyses on. We would do a gold fire assay, but we would also run the pulp with a teraspec, so we get the shortwave infrared response for that. That was our toolkit, okay, for exploring these types of systems in South America. Now, later on, when we got more into the continual scanning technologies like core scan, we ran the core scan down, I think, the first 80-something holes from top to bottom at Alturas. So we ended up building up, obviously, like a pretty detailed, we tried to get as much value out of that data as we could, but in all sorts of models in terms of the various mineral chemistries. Now, when it came to the surface work, so before we drilled, we also used some of the airborne and satellite imagery as well. We had astroimagery that basically helped us identify where the alunite was and map some of the light zones as well. But on the ground, we would look for the variation in the chemistry of the alunite. And one of the things was to track the aluminum of illite. So that's something you can see spectrally. We would also track things like the crystallinity of illite. The way I see it is that chemistry, and you'll probably correct me now because I'm probably wrong, but just as a simple sort of exploration geologist, the way I envisage something like shortwave infrared helping us in the field is that the crystallinity is telling us something about the temperature of the fluids, or implying something around the temperature of the fluids. And the chemistry of whichever mineral you think is your sort of indicator mineral or your main ubiquitous alteration mineral, the chemistry of that mineral is telling you something about the pH of its formation. So if we're looking for hot acidic fluids, then I'm looking for high crystallinity minerals, and I'm looking for certain mineral chemistries. If it's aluminum rich illite, then that's one thing. If it's potassium alunite, it's another thing. If it's sodium alunite, it's another thing. We also found, by being involved and participating a lot in some of the collaborative research projects, that there was different phases of quartz or silica alteration also had different chemistries. Now, the geologists in South America, or the barrack geologists anyway, already knew this, and they documented it actually in some papers about the discovery of Pueblo Viejo in the Dominican Republic. And they, in those papers, talk about what they call sílice parda, which is dark silica. They talk about this dark silica, and when we ran a bunch of samples from, I think it was Veladero, as a test case in one of the Amira projects, they looked at the crystallinity and basically if there was any variation in mineral chemistry of the quartz. And they found that there was a quartz phase that seemed to imply fertility of the system, so whether it was a gold-rich system or not, when the quartz had titanium in it. So the quartz have little blebs of titanium oxide, so little rutile blebs in there, and it would make it look darker. So as a field geologist, they call it sílice parda. You send it off to a lab and get a whole bunch of researchers involved and Aussies, and they called it rutilized quartz.
Oh my.
But it's the same thing. But what it means also, if you think about it, is that if titanium then was mobile in the system, you're
Uh-huh.
talking about pretty low pH fluids in any
Yeah.
case. But I think personally, there was always a debate internally in Barrick of how mobile the titanium really was. And my view was certainly that yes, it would be remobilized, but I think just on quite a local scale. Now, there are people who disagree with me about that, and that's fine, but just giving you my perspective of that. So if you start dissolving some of the minerals, some of the hornblends and the biotites and things in the original dacite rocks, then there's titanium, and maybe there's some other titanium bearing minerals too. And then I think that titanium was just only remobilized quite locally and was incorporated in the quartz when the silicification was happening. I don't necessarily think that titanium was introduced from somewhere else. So you're looking for
Yeah.
siliciparda, you're looking for potassium alunite, you're looking for aluminum-rich illite, and good crystallinity, basically.
Yeah, and I'll just add a few flavor flecks in here for people that have some desire for more knowledge on some of the spectral things. When we talk about crystallinity, we're talking about the orderness of the crystal structure. Is it really formed under higher temperature? Therefore, the crystal structure is more ordered. What we use it for is a proxy for temperature. So illites being, for instance, less crystal structure
Yeah.
ordered, lower temperature kind of thing. And the other thing is when we talk about using terror specs or even using any kind of scanning systems with pulps, you just have to think about always the size of the aperture, the pixel size, and are you going to get a good sample in there? So if it's a pulp at 80 mesh, we'll say, but your pixel size for a terra spec is 1 centimeter or 2 centimeters, even a core scan instrument at 250 micron, are you going to be able to, yes, of course, you'll see you got chlorides, you got white micas, you got kaolinites, but you might not be able to get down into the fact of what are you seeing internally? Are you seeing a potassic alunite versus a sodic alunite? So like it's really important, and I know we're going to talk about scale in a different way coming up, but it's important to think about scale when you think about what you're going to do in terms of using those types of instruments. I've had a lot of success. I've seen a lot of success just doing soils, but before you've sieved them or anything, and just looking at it, just pouring it out over a long, say like over a meter in a core box. We scan that soil, and yes, and say a high sulfidation system, you see mostly iron oxide. But what you're looking for is some of those, we can call them maybe some of those indicator minerals, some of those really trace minerals in there that might give you something really interesting. You'll pick up tourmalines in there. You might pick up some micas in there, some kaolinites. But if you have kaolinites and then you all of a sudden you make it to, okay, and now I'm seeing some alunites, well, now you can see how you're moving towards maybe some kind of hotter center or lower pH center. So I definitely would say for sure, look at soils, look at things that are a bit more coarse grain, but the pulps overall, I just haven't seen a lot of success in them in terms of really getting down into crystallinities, into chemistries. But if you're just looking for general groups, then sure, that's okay. Anyway, that was my little aside. You guys couldn't see me making all the different hand movements. It's the Italianness and the New Yorkness in me that does that. But if you guys could see it, my hands are moving all over the place, and I think it would add some flavor for you guys to know that. Okay, so we've been talking a little bit about scales then, so let's continue down that path. In terms of regional to camp to target delineation, what types of geochemical and spectral tools can one employ to aid in discovery?
Yeah, well, on the regional scale, the thing is the gold can be, well, it is pretty much encapsulated or can be encapsulated in the silica, so in the quartz, and it's very fine grained. So we found that we could not see, for example, stream sediments surveys, we could not see even outcropping mineralization more than just a few kilometers away.
Wow.
So a regionally spaced geochem stream sediment program, you're not really looking for, I mean, okay, you're looking for, because you might come across one, well, pretty much, you know, fortuitously, gold anomalies, but that's not necessarily the first order thing you're looking for. In the paper, the image we used was actually the lead in stream sediments. And if you look at that figure in the paper, you can see that all of the deposits in the belt, so El Indio, El Tambo, and Alturas, are all lead anomalies in the stream sediment survey. Now, lead is quite interesting because something we didn't mention just now when we were talking about mineral chemistries or mineral chemistry research was that we found that, again, in samples that had, well, basically, the potassium alunite had a certain lead lanthanum ratio that seemed to indicate the difference between the sizes of deposits. So I said that the titanium in the quartz indicated whether it was a gold fertile system or not, but the lead lanthanum ratio in the potassium aluniite could indicate whether it was going to be a giant deposit or just like a regular deposit. Because Pascualama and Veladero and Alturas, I think, as well, all plot with high lead lanthanum ratios, and the other deposits don't. So it's kind of interesting because we got, now I'm not saying there's direct cause and effect or anything, but it's interesting that you end up with lead anomalies, and the lead was the element that we chose to illustrate in the paper. And the alunite from the system is high in lead or on a lead lanthanum ratio compared to others. Now, when we came in close to the deposit and we had, so when we were doing systematic sampling, so for example, I think we did a rock chip grid. I can't remember if we did soils or not, but there's a lot of outcrop up there. I mean, it's partially concealed. We called it in the paper, the deposit, but it's concealed by its own volcanic pile, basically, right? And of course, you're in the high Andes, so there's outcrop. There's scree slopes and everything, but there's also a fair amount of outcrop. Anyway, so the sampling we did there, we sampled the scree, but we also sampled the outcrops, and we would screen. So again, using the shortwave infrared instrument, we would screen for the samples for potassium alunite. I'm talking about now statistically. So we would pull out statistically, filter out the samples that were high, that had high potassium alunite, and then we would calculate the lead lanthanum ratio from the ICP, the 4-acid digest ICP, in those samples. And that became another exploration tool that we use. Now I'm talking about it now because this was 6 or 7 years ago. I think I can probably talk about it. It's probably been written about or spoken about in public before. But these sorts of tools that we've been talking about, they were developed by these collaborative research projects. It's really important. There's a lot of large companies participate in these research projects, and they're very important in terms of generating new tools. And it's not just geochemical or spectral tools, but they have the same thing from drilling, they have the same thing for geophysics. And this is a really valuable part of our industry, and it's really good that they continue to be supported by the big companies. So these tools that come out of those, then they're exclusive for the sponsor companies for a while, and then sooner or later people start publishing papers on these new tools when the confidentiality expires. Anyway, I got on a bit of a limb there, a bit
Love
of a
the
rabbit
limb.
hole. But I guess the point I was trying to make was that at certain scales, you just got to think about the nature of the mineralization you're looking for, the type of, and the size of the alteration system that you're hoping for relative to how exposed or covered it is, and then what elements might be working at certain scales. And then get a bit clever about when you're doing your data interpretation and your geochem modeling, that you can filter out certain samples and focus on certain other samples. We're looking for what they call anomalies, right? We're looking for unusual things. So we don't necessarily have to treat once the samples are being collected in a systematic way, once we have the data, then we can slice and dice it pretty much any way we want to, and we don't have to treat them all the same. And we're trying to increase our chances of finding the unusual part of the survey area.
I love that. And I just wanted to follow up by just asking or stating, and then maybe you building on it slightly. I found really interesting in both what you're talking about and reading in the Storga paper again, how there you guys were looking at anomalies in different data sets. We're including the black magic geophysics in here as well. And you're applying this into process-driven exploration. So, for example, you're using resistivity to look at, okay, well, this actually is mapping our Voge silica. You're using Aster, looking for your sulfates. All these things were just so interconnected And I think a lot of it's just never having worked in a big company, but I never really appreciated just how well this was all working together in your guys' exploration for the 10-15 year period that this paper covers in Alindio belt.
Yeah, it was interesting you mentioned. I'll just pick up on that time factor that you mentioned at the end, because this was an area that had already been explored by that company and actually by some of the people who were still working for the company all 10 or 15 years before the discovery. And one thing that actually did impress me with the whole process was that management was still pretty open-minded about going back and reassessing an area that had already been written off by some of them, actually, all that time ago, because we had better tools. So the thing is, you say, well, why would we go back somewhere? What are we going to do differently? But now we understand more about mineral chemistry, or now we've got better resolution electrical geophysical instruments, or now we know more about the spectral response of these things. And so, okay, well, we'll support you then. You go back, put a program together, and walk the project again through the various exploration stages and scales, but on a process-driven basis. So recently, I say recently, over the past probably year and a half or so, I've been asked by a few clients, probably 3 or 4 separate clients now, to help them put together or to help them organize, right, their exploration project pipeline, essentially, right? And what I find when I go in is that companies, they want to have as many anomalies, quote, and I'm doing the quote unquote thing for people who
Love it.
nobody can see me doing my
Yeah.
hands either.
Maybe
So
I'll make that like the picture for the episode. Yeah, that was a good
yeah.
one. Now I'm doing
Um,
it too.
Yeah, but the thing is, right, is that they got all these anomalies. And say, oh, well, we've got a resistivity anomaly here, or we've got a conductivity anomaly over here, and we've got a lead anomaly, we've got an arsenic anomaly. And you're just going, what's that got to do with anything? I'm not, what's the conductivity price today? Well, there isn't one, is there? We're looking for gold, we're looking for silver, we're looking for copper, uranium, all these other things. So it's like, what is the process that's going to lead us to a discovery? So as you just mentioned there, right? We're looking for resistivity highs because we're looking for a great big chunk of quartz in there, or silica, silicification. So sometimes if you look at the papers that have been written on Pascua-Lama as well and these other high sulfidation deposits, there's a huge resistivity high, okay, that's basically subhorizontal because it's mimicking that water table or that water table interaction zone, and that's where all of this action was happening, all of the leaching and then the vuggy silica and then the silicification of everything. And it happened over, broadly speaking, a horizontal sort of uh, zone, right? And so, and then in other places, you're looking for things that are vertical. Maybe you're looking for breccia pipes and diatremes or great big quartz feeder veins. So then those will be more vertical type resistors, won't they? Now, the thing is, there's not enough interconnectivity of the sulfides to really have a big chargeability anomaly. So you might run IP and you might have a chargeability anomaly, you might not. But you got to think about the process and why you don't or why you do and what it might be indicating. So again, we're not looking for pyrite ore bodies. We're looking for, yes, pyritic and sulfidic ore bodies that have gold and silver and copper and all the other stuff in it that we can sell. So all of these exploration systems that you mentioned, like in the larger companies that have had these systems established for a long time now, they're largely process driven. So don't talk to me about an anomaly here, an anomaly there, and a high and then a low and a mag high within a mag low and all this. Tell me what you think that means, right, in the context of your rocks.
Yeah, this whole concept too of ore body knowledge is so prevalent in big companies and just
Mm.
yeah.
The advantage that any producer has is that obviously they have deposits that they can do as much or as little research on as they like. So if you got a large company, they got a lot of deposits. When I started working for Barrick, they had 27 mine operations. I remember that number because they had 27 mine labs, and they said, well, part of your job is to audit the mine labs. And so I knew there were 27 of them. But you have all these other big companies that have all these operations, and some of them are huge. So the more you understand about the deposits you're already mining, you've already found, okay, then you can do orientation surveys, you can do other studies, you can have research projects, you can have PhD projects or whatever, or you can have just company geologists mapping and company geophysicists and other technical specialists doing orientation surveys and little mini projects and stuff to better understand A, what the processes are, and B, what the responses to those how do we find or detect these processes. So you end up with a very process-driven sort of exploration program. And the language or vernacular within the company is certainly at the exploration meetings, these peer reviews, becomes a lot more discussion around what processes may or may not be going on in a particular project or target area, rather than just people talking about statistics and highs and lows and things.
Such a good point. I wanted just to take a super quick sidebar because we keep talking about alunite, and just for all of our listeners out there, when you talk about spectral geology, we're looking at part of the electromagnetic spectrum. We're looking at, in this case, Venus were 450 to 2500 nanometers. At 1480 plus or minus 10-ish nanometers, that is the absorption feature of alunite, where you can see a change in mineral chemistry between the potassic to the sodic end member, which is the longer end member. And that's how we're differentiating between the two. I forget what the name of it is. It has a whole different name, but the calcium rich end member for alunite is just something, it has a completely different spectrum. So you won't get that confused. It has a weird name. I feel like they changed it. But anyway, that's how we're talking about it, like it's no big deal, because now it is no big deal, because now you guys all know about it. Moving forward, I was thinking, okay, so something that I encourage people to think about when looking at data sets is to think about what phases the mineralization is hosted in, therefore helping them to select element suites when we're looking at our trace element chemistry. So with that in mind, what is this suite of elements that we should be looking at in our...
Yeah, well, this question, it's almost like a traditional question that people ask at a certain deposit styles, like, oh, what's
Yeah.
the suite? Oh, what should be, again, yeah, sort of anomalous.
Mm-hmm.
But the thing is that, again, like I said, we're looking at geochem data anyway. There's this term, exploratory data analysis, that was coined back in the 80s, I think it was, by the old CRA geos. Just see what the data is are telling you, and then try and link it to some geological process. So the thing is, you might have bismuth, you might have tellurium, you obviously have a lot of sulfur minerals, but you might have copper, okay? You might even have lead zinc. I mean, there's sphalerite in the system at Alturas, and actually there's sphalerite chemistry also changes. You've got more iron-rich sphalerite, and then you've got less iron-rich sphalerite. And it seems
Interesting.
to also vary on a sort of depth basis. Part of the high sulfidation sort of mineral suite is you have things like energite. You might have other sulfur salt minerals as well, again, because you've got so much sulfur around, right? So if you've got tennantite and tetrahedrite, then you'll have copper and arsenic and antimony basically coincident with your highest sulfur, okay? And then, because they're garbage cans of minerals anyway, you could have all sorts of other things stuck in there as well. They could be high in mercury, they could be high in tellurium, thallium, or just about almost anything else. So it depends where you are in the system. I think at one point we were looking at the Geochem Alturas, and I said, oh gosh, you know, it looks like there's a bit of a bismuth sort of association with the mineralization at depth, but still in the ore zone. So if you see that in the early stages of drilling, and if you mention that in a room of other experts or people who are a multidisciplinary sort of room, then somebody might perk up and say, oh crap, we don't have to run bismuth through the plant. That'll screw with the recovery, or that'll mess with that, or if it's in the waste, we can't stick it over on a waste pile without some remediation. So then you socialize that in the group, and you might get ideas saying, okay, well, where's the bismuth? So in an early stage drilling project that looks promising, that's a flag. And you might say, well, okay, you know what, we're going to have to do some testing on this. We'll have to do some find out what the actual deportment of bismuth is, how closely it's associated. Is it going to go into the ore stream? Is it going to go into the waste stream? And that is something that when we develop the project, or when we move the project through the pipeline and we're doing something like a scoping study or a pre-feasibility study, that might be something that we'll have to consider doing some additional work on. All right, so we're always thinking about planning for success, and if this project moves forward, what would be the next set of questions that would be asked? And when you see minerals like that or elements like that that are associated with some of the mineralization, or is either very close or within the mineral zone, then you want to try and work out what the minerals are that contain those elements. So that was a long-winded answer that didn't really answer your question. But yeah.
No, I think you, in a roundabout way, hit on exactly the point, which is that when you go into iogas, there will be that suite of elements that they recommend if you're looking at a high sulfidation project that, okay, these are the top 10 elements that you should be looking at. But it comes back down to every deposit's different, and you might have this mineral phase in there that makes bismuth, for example, a good element to use while you're looking at things. So you just have to keep an open mind when you're doing things. And I think that's really in the spirit of the answer that I was looking
Yeah.
for.
I mean, generally speaking, when you're close to the paleo surface, all you've got is this really sugary, sort of powdery quartz or silica. Okay, they call it steam heated alteration. So when you go to a mine like Veladero, the paleo surface is right at the top of the high wall of the pit, and it's pretty windy up there, right? So you get up there and it's like snow blowing around, but it's bloody silica, right? So everyone's wearing a respirator, or you don't get out the bus. You walk around the rest of the district and you come across these sort of fairly large areas, a few tens of meters by 100 meters or so, things like this. And it's the steam heaters, this really powdery, very white silica blowing around. And if it's in outcrop, it almost looks like a kind of reef or something. You know, it's a very craggy and porous looking. So up there in the steam heated zone near the paleo surface, it's pretty much dead from a geochemical point of view. It's this steam heated, fluffy sort of silica. Of course, as we get down and you start drilling, or if the exposure of the system is a bit more eroded, then you'll get closer and closer to hopefully to the ore zone, and you'll start seeing some actual elements that you might call pathfinders, like mercury or something, or you might start kicking in some arsenic and antimony and stuff like that. And when you get through to the main ore zone, often is when classically, I suppose, the base metals will kick in a bit harder. So you might start to see a bit of a copper increase towards the bottom of the ore zone or underneath the ore zone. But again, I would say encourage people to just think about the minerals that you might see. Where would you get copper? Why might you get that in? Well, it'll be in energite and minerals like that. Probably not in minerals like bornite or chalcopyrite, but just thinking about what that might mean for where you are in the system. From an alteration perspective, we're mapping mineralogy,
Yes.
but we're looking for elements. So we're using one thing to infer another, and we analyze for elements. So we're using the elements to infer mineralogy, so it'll help us in our mapping of the alteration to eventually find some gold that we can extract and sell the element back again. So it's all part of the process.
I wanted to chat really quickly back again at the Astorga paper. There's just a lot of work that you guys seem to continually run over the Alturas projects, even when arguably you had made the discovery. And so, for instance, you guys ran an orientation survey over it. Why would you do something like that?
Yeah, I'm glad you asked that question, Sam, because, well, for two reasons, actually. We sort of touched a little bit on it earlier as well. So the thing is, one thing that we managed to do in Barrick, and again, got managerial support, so that means dollars to do. And it first, as well, the first one I was involved with was the gold rush discovery in the Cortez district in Nevada. So that's another deposit. I think when it was published, the first resource published was about the same size as Alturas, about just shy of 7 million ounce deposit. The grade was a bit higher because Carlin deposits grades are normally higher than the high sulfidation epithermal deposits. But the reason why I'm mentioning that is because after that was discovered, we managed to convince management to support an extensive orientation survey or suite of orientation surveys over the top of it. And that was both geochem and geophysics, because the Gold Rush ore body it's covered, all right, but it's subcropping. So it's covered by these, what they call the Carlin Formation. We're not getting too deeply into that at the moment, no pun intended. But
I got
anyway,
it.
it's only a few hundred meters of cover, but largely unconsolidated cover, some volcanics and stuff. But then the actual sort of hard rock base, the cover bedrock interface, there's the paleo exposure, if you like, of that deposit. So I was like, okay, how would we recognize that from just doing surface geophysics and surface geochemistry? So we'd already done that. So we had a little bit of a history, we had a little bit of a precedent set in the company for running a big orientation survey. And the budget for this just the geochem part, I think, was about $100,000. We're talking about 12 or 13 years ago. That was a lot of money to ask for in an exploration budget to just go out and find something you already found. So anyway, when the Alturas discovery came along, basically the technical team managed to put forward a proposal that was accepted to do a similar orientation survey over the top of it. Because there's this terminology in the paper, we talk about semi-concealed, I think we use that phrase. So essentially, the ore deposit itself, if you look at its sort of vertical projection to the surface, yes, that's covered. Yes, it's under a couple of hundred meters of volcanic cover. That's part of the same volcanic system. However, the relief or topography there being so severe, there are actually cliffs where the silica alteration is outcropping. And if you sample the cliffs, you'll get 1, 2, 3 grams per ton out of some of the samples that you take along these cliffs. But the deposit itself, but that's kind of, well, okay, there's various interpretations, whether that's leakage or some sort of lateral expression of the ore body. But the ore body itself is undercover. So, yeah, we put in the proposal and we got the budget to do the orientation surveys over the top. And that's where some of the conclusions or things that came into the paper came from, when we look at a little more detailed analysis, if you like, of the spectral geology and of the geochemistry and the geophysics.
Was there anything that you necessarily found that you could see?
Yeah, well, I was back to, again, in my mind anyway, sort of consolidated the thinking on the illite chemistry, on the alunite chemistry, but also the how to really integrate the geochemistry with that.
Yeah.
So instead of then necessarily having to go out and do SEM or ChemScan and things like that on these concentrates, which is time consuming and expensive, we figured out that if you, like I said, if you do a 4-acid digest and you got really good analytical geochem, then and you use the TerraSpec at the same time, and you basically, in iogas, you switch off all the samples that don't say alunite as the principal mineral. Then you switch off all the samples that don't say potassium alunite, so you're left with just the potassium alunite. And if you do that on the filter feature in iogas, then it doesn't use any of the statistics for what you've got filtered off to work to do the rest of whatever else you're going to do. And so then you work out the lead lanthanum. I think there might have been a couple of other element pairs ratios, and plot those diagrams up and say, right, this
Interesting.
is an exploration tool. And it was successful. It was so clear as an exploration tool that after that, when we were doing our budget presentations to upper management from Toronto, they would ask, if we didn't show them, they say, where's the lead lanthanum in alunite map? Who knew that would be a thing?
Awesome. Yeah.
It's a household name,
Yeah, exactly. Oh my goodness. That's
Yeah,
lovely.
yeah,
I
yeah.
love that.
So yeah, that was kind of just how we rolled, I guess. It was a really good, it was a really good experience. We had a lot of support for technical work, good technical work, and then we had support for furthering that work either in-house or with collaborative research. And I think it really did help and contribute towards some of the discoveries that we were able to make.
What I really love about this story, and not to put down geophysics or any geology, et cetera, but I have a lot of people that ask me, whether now consulting or back when I was working for CoreScan, like cheekily, people would ask me, "So now that you work for in spectral geology, what do you think is better, and what would you choose? Would you still do geochemistry or spectral geology?" And I love how a lot of the story that we've been talking about today is just talking about how these two disciplines and the other ones that we've been talking about, geophysics, geology, et cetera, that they're better together. And I really love that as part of this whole story.
Yeah, was back to, so I'm going to just harp on about this, the process-driven approach, right? So the
Yeah.
more data I have, okay, so there's going to be diminishing returns, okay, but essentially, well, I don't think I think that most projects are not there yet in terms of having the minimum appropriate data. We can still do better. So, for
Mm.
example, one thing that's come up recently, and actually not really recently, but we've been thinking about it for a while, discussing it with a couple of clients at the moment, is that yes, when I do the geochem interpretation, I say, well, okay, give me all of the geochem for each sample. Okay, give me in the data extraction, give me the XYZ locations. Okay, give me also as much of the logging data or information that you have. So give me what you think the lithologies or formations were. Give me, at least if it's just a discrimination between whether they're crystalline rocks or sedimentary rocks.
Mm.
Okay, give me your best stab at the alteration for each sample. Okay, in the extraction. Now, give me any spectral data that you might have, point or spectral data that you can consolidate down into a query on a sample interval. But also, what I tend not really to see much of at all yet is, or it's very sporadic and hit and miss, is petrophysical data.
Mm. Good
So give me
point.
the mag sus for all the samples, right? Give me the conductivity if you've got it for all of the samples, okay? And then we can start, okay, because from the geochem interpretation, I'm going to start inferring potentially, oh, I think this is where the magnetite is, or this is where the pyrrhotite is, okay? Just looking at various ratios in the geochem. Well, if I also had magnetic susceptibility for all the samples, I'd be able to say, oh, and it's the magnetic material. So before we go and do the field validation at the core shed. Okay, so I have worked on one or two projects where we've had MagSus in orogenic deposits over the last 2 or 3 years, but it's certainly, I wouldn't say it was anything like a systematic or SG, density, specific gravity,
Mm.
anything like that, because it's going to help us pin something to a process. Because as you know, when you look at, if you've got 50 elements and you start plotting them against each other, or you throw it into some sort of statistical process, like a PCA or a k-means or something like that, then you're bound to get some things correlating with each other, but cause and effect are not necessarily linked. Actually, I came across a few diagrams the other day, and there's these two curves. It's a graph that goes over about a 10-year interval, and these two curves are almost coincident. They very closely track each other. And one of them is the number of movies Nicolas Cage starred in each year, and the other one is the murder rate in the US.
There is
Clearly not
correlations.
connected.
Yeah, yeah, yeah.
Clearly not connected.
Yeah.
Yeah. You can look up silly graphs like that and put them into presentations or lighten it up a bit if you wanted to. But really, just because you have two things that sort of track each other doesn't mean that one is the cause of the other or one's an effect of the other. So um, you just want to, again, try and put it back to some kind of process. So if it's elements that you've tested are immobile or conserved in a system, so they're reflecting the original lithology and they were not affected by alteration or subsequent processes, then you use those, and whichever ones you come up with, you have to be able to tie them back to some geological process. And then if you come up with a PS element ratio or something that seems to be working in your deposit that shows you that can map out some of the alteration, again, you have to ground truth it. You have to go back and tie it to a process. There's no point in saying, oh, I've got albedic alteration in a high sulfidation system. It just doesn't make any sense.
Mm.
You can't say, oh, my sodium is high, so therefore this. No, because you're not tying it back to a plausible process. And then the same thing comes with the mineralization. If you look at the sulfide geochemistry, or what is sulfur correlating with, what are the elements that are high in certain iron sulfur ratios and things like this. You need to start piecing together what the sulfate, sulfide chemistry is, but it has to be linked back to a process. Again, it's not like you're going to say there's a massive sort of bornite body down there in the middle of your pH 1 zone, right?
Indeed.
It just
Yeah.
doesn't make any sense. If something can't be tied back to a plausible geological process, then basically it's a red herring. All right, don't even mention it in the final interp, right?
Yeah.
Yeah,
Lie.
no, just don't mention it. Gosh, there's lots of things I don't mention, Sam. And life's just fine.
Oh my God. Look, I have one more question for you. We've touched a bit on some of the problems that we can happen with geomet, but and maybe I'm being a bit cheeky here because that's just
You
how
cheeky.
yeah, exactly,
Whoa.
because maybe I'm thinking about one situation specifically that will not be mentioned. But I just want to just add is that environmentally, is there anything really important in these very acidic systems, lots of sulfate, et cetera, to follow up as part of your initial study so that when you go to make a mine, you're in the clear?
Yeah. Well, you're never in the clear, really, are you? Right.
You're never in the clear, but maybe so that your permit goes through.
Yeah. Well, I would say that just as a general comment, again, just about things that certain groups do better than others, is that, again, I've gone to a lot of projects and people are sampling in and around the ore zone, and their sampling protocols are, if we see veining or if we see this type of alteration or this type of lithology, we sample, and then we sample 10 meters above it and 10 meters below it in the hole. So what that means is that you have no idea. Again, if you're planning for success, that's not really planning for success, right? Because you're going to have to move. If this is open pit, you're going to have to move all the crap that's on top of it. So you need to know what's in it. You need to know the waste. You need to be able to do the waste characterization. Of course, it's a little bit different if you're going underground, but you still have mining widths which normally will always exceed the width of the ore body. So you're still dealing with waste rock. So when you're not analyzing all the rest of the rocks in the holes, you are not you're not putting yourself in a position where you can successfully characterize the waste, which means when it comes to permitting, when it comes to what on earth am I going to do with all this waste, then you've got to go back again and do some metallurgical sampling or waste characterization sampling and things like that. Now, critically, we're talking about a high sulfidation system, so pretty much by definition, you can have a lot of sulfur kicking around, and of course, sulfur plus water equals sulfuric acid. So you've got a lot of rock that you want to know whether it's potentially acid generating or not. That would be I think a big item. Now, if you've got potentially acid generating rock, how are you going to neutralize it or isolate it? Because, of course, we're talking about volcanic settings here, so it's not like you can have a great big limestone hill, pure, fresh, beautiful, pure, pristine limestone hill next to your mine that you can just use as to buffer your potentially acid-generating material. But also, what are the other elements that are in there that now or then might become mobilized if you've got a great big pile of rock generating sulfuric acid? So it's where you come in, then you say, well, if I've got sulfur salts, which are very soluble, generally speaking, and so make a lot of, and earlier I mentioned them as a garbage can of elements. So if you've got a garbage can of elements, so basically with the lid off, what is going to leak out, right? So where is the tellurium? Selenium, that's another big one. It's literally a killer for aquatic life. So any riparian habitats, any aquatic, that's a big one that you need to get a handle on. How would that be mobilized in whether things are potentially acid generating or not? Okay, so I'm a big believer. I think when I worked at Rio, obviously Barrick as well, but even back in the days when I was working with Kennecott, Rio Tinto, a big part of our project evaluation, especially on the advanced projects, was waste characterization. if you think about an open pit, the stripping ratio is never less than 1. So you're always moving more waste than ore. So really, a
Great
porphyry
big mess.
deposit a porphyry deposit is a great big granodiorite mine with some copper at the bottom of it.
Indeed.
Yeah.
Yeah. So there you go. Well, thank you so much, Simon, for being here. And I hope that everyone out there listening got at least some new ideas on how to tackle their high sulfidation epithermal programs. Thank you all for listening to Geochemistry. Big thanks to Simon Griffiths for stopping by the show for a second time, dishing some more tea, and taking us on another ore deposit and geochem journey. Thanks to our sponsor, LKI Consulting, and to It's Water and Coma Media for our music. And I'm looking forward to chatting with you all next month, where we'll be discussing critical metals and acid mine drainage.